Thank you very much. Can you hear me? I turned it on, but I'm not sure whether that's what you do. Okay, it's a pleasure to be here finally. I was able to meet nature and travel here to College Park. As you may remember, I was supposed to be here in April of again this year, but I was stuck in England because of ash clouds from the volcano in Iceland, so I had to cancel my trip back home. And it's this tells you that actually the nature sometimes is not, and most times is not friendly. So, and this is something we always try to model into any design, and that's what robust design is all about. But sometimes the nature is so powerful that you cannot do anything, and that's something that we have to realize also, that it's not always to build systems which will work all the time. Sometimes in extreme cases they may not. So today's, and I should say I'm very pleased to be here at the Institute for Systems Research, and I know the 25 years ago, I believe it was 25 years ago, when it was founded, and we were all excited in the control community because this was one of the 6 ERC centers and an institute in systems research and control communication signal processing. To be on that short list was made all of us proud. So the institute has matured, definitely, but I would say that it's 25 years old, 25 years young, because it has really during this day, talking to different people, I have realized that there is still a lively environment, research environment producing, and so I'm sure it will take it down the road another 25 years at least, and even longer. The title of my talk is Sensing, Control, and Decision Making with Limited Actions. And this is actually only part of the talk. This is in the second half. I'll be talking about limited actions. And what I mean by this is actually limits on actions. There is a certain limit on the number of times the controller or the sensors can act. And the question is, how do you formulate problems of this type? But after coming here, actually, I realized that maybe I should use a different title. And what I would have used instead is the green sensing, control, and decision making. And I have seen so many there, and this is something very constant, of course. There are all kinds of efforts to make all the designs and environments and the usage of our green and be cautious and don't use anything unless you have to. And that's in essence the one of the messages that I want to give here, because I will be saying you should use control. The controller should interact with the system only if it has to. The sensors have to be awakened and send signals only if they have to. And the question is, how can you formulate these problems in a mathematically precise way? But I think the green sensing and the greenness goes very well with this, because that's power aware and which takes into account the restrictions and conservations of energy, as well as any restrictions that on battery power. So the outline of the talk, when you talk about sort of generalizations or extensions of the paradigm that is used in control theory and in signal processing in some sense, to more realistic scenarios when you have limits on the number of actions, the number of decisions that one has to make, you inevitably run into non-classical information. So I want to spend the first 20 minutes or so, maybe 25 minutes on sharing with you some of the sort of historical trends on problems with non-classical information. And what are some of the caveats and counterexamples, why some of these problems are tractable, some of them are not tractable. And then I'll move on to talking about leaving the current paradigm of when we design systems, control systems, we talk about how to shape the signals and what to send. And in addition to these, I would like to pose the question of when to send and whether to send. And so that's a discrete decision, whereas the others are continuous decisions generally. So I want to say that these are sort of hybrid decision-making problems. So I talked about variations around the common paradigm, a network control system. So this is something which is familiar to all of you. It's a feedback system, and the difference from the standard setup is that now you have the sensors are connected to controllers over a network, and the controller is connected to a plant over the network. But what I mean by plants here is something more general than what we think of as a physical plant. I'm thinking of multiple agents, actually, that are distributed over a network. They interact with each other, and they use limited information during that interaction, both online and offline, and under possibly conflicting objectives. So whenever I talk about a plan, you have to view it as a much more general object, not necessarily a physical plan, but a collection of agents, and they interact with each other, and so there are feedback loops within the system. Now, when we look into different sort of variations on the common paradigm, there could be, and when you link network between the sensors and controller and the plant, then you may have failures in the channel. That has to be taken into account. The failures could be of probabilistic nature, and so the statistical sort of description is one, or they could be of adversarial nature, which means a jammer. A jammer could disrupt the communication. And another variation is that you will have delay and limited memory and decentralization. And so the transmission could be delayed, and that will affect the way the decisions are made. Or there will be limitations on the memory that the controller will use, and as well as decentralized control in this general multi-agent framework. And the channels are generally digital, so that will require quantization, both from the sensor to the controller, as well as from the controller to the plant. So when you digitize signals, then of course you lose information, and the question is, within a given limitations, what is the best quantization scheme, for example. And then another extension of the standard paradigm is to replace a single objective function with multiple objectives, and you have non-cooperative controllers or agents, and then that brings us into the paradigm of game theory. And then finally, and this is the main towards the end of my talk, I'll be talking more concentrated on this extension, which is a limited usage or the limited action. What I mean by this is that the sensor, for example, will communicate with the control sparing. There are n time slots, and so which means there are n opportunities, but the sensor is allowed to communicate with the controller only m times out of n, where m is much smaller than n. And you could have a situation where the controller communicates with the plant only, also intermittently, and again it would be m out of n times. And then another extension is where the jammer would disrupt the communication between the controller and the plan, again intermittently. So the general framework in which all these problems are addressed is first of all, we have multiple decision makers, agents or players, these are synonymous. They pick policies, which decision laws or strategies, which lead to actions that evolve over time. And the policies will be constructed based on information that's received by the agent. They could be active as well as passive. And by active information, I mean information that depends on what the other agents have done. And by passive information, information that is collected from the environment that is not necessarily affected by the agent's actions. And the construction of the policies will be guided by individual utility or cost functions over the decision-making horizon. Now, if we have, as a special case, a single decision-making problem, if there's only one decision maker, this would be a collection of agents, but they all share all the information, and then there is a single objective function. Then we are in the realm of stochastic control. If there is a single objective but decentralized information, then we have stochastic teams. And otherwise, the most general problem is either known as zero-sum games or non-zero-sum games. And in the case of non-zero-sum games, Nash equilibrium would be the natural sort of solution concept. So I mentioned this difference between passive and active information, and the question is of course, if information is affected by actions, then those actions in turn, that information will lead to construction of new actions. So there is definitely a coupling between information and actions. So if we ask the question, is the quality of active and relevant information received by an agent in this scenario, is it affected by actions of other agents? If the answer to this is no, then we are in a sort of a static environment, and the problem is generally simple. By simple, I mean tractable, the meaning of this will become clear. It doesn't mean that it's not a problem worth looking into, but the level of difficulty is not at the order of the level of difficulty of the other problem case, which is if the answer to this question is yes, then it's a generally a difficult problem. So what I want to discuss for the next 10 minutes or so is the simplest problem with non-classical information. So these are the problems where you have limited, any control problem where you have limited memory in the controller is necessarily leads to a problem with non-classical information, as I will make clear shortly. And the simplest possible problem is the following. You have, in this case, essentially two decision units. So you have to come up with something that's interesting. You have two decision units, A and D. And that here is a channel. For those of you who are reading information theory, this looks like a Gaussian S channel. And you have a random variable, which is Gaussian zero mean variance sigma x squared. And then this random variable is going to be shaped. We could call this an encoder also, and passes through a Gaussian channel. W is independent of x. And then the measurement y is received by the second decision maker who has to shape it and then come up with and you can introduce different types of measures, and Q stands for quadratic here. And so I'm looking into different sort of quadratic functions of these variables, x, u0, and u1. And then given these policies, gamma 0 and gamma 1, then you have a cost function which is defined on the strategies spaces. And the problem of interest for a given quadratic function of this type is to minimize J. Now, to this problem in its most generality, we can write out the general quadratic function, But that one is not solvable unless you consider some specific cases. So this is a problem with limited memory because essentially and one with unclassical information because the second decision maker does not have access to the variable which enters into the decision unit of the first decision maker. If I had a feedback or feed forward from here to here, then this would become a classical problem. So the simplest difficult problem is the one which was in this framework formulated by Witzenhausen in a SIM paper in 1968, and which is known as the Witzenhausen counterexample now. Now, those of you who have read that paper will remember a different formulation, but what I have here is a transformed version of that problem, which is equivalent to the Witzenhausen problem. Just simply some transformation of the variable. So the quadratic Cox function in the W stands for Witzenhausen is essentially one that consists of two terms. U0 wants to be as close to x as possible, and then the U1 wants to be as close to U0 as possible. Okay, so that's it. And note that if to minimize this, you have to pick separately. If you had only this term, then you would pick U0 equals to x. But picking U0 equals to x would not necessarily be the best solution as far as minimizing this one. So what Witzenhausen has shown is that the optimal T solution in this case exists, but its structure is not known. And he posed this as a difficult problem, and since then the problem has not been solved. At least optimal solution is not known. And what is known is that the affine policies are not optimal in this case, or in this case the linear you can any optimal affine policy would also be a linear policy. And now the difficulty here is one observation is that if you restrict to affine policies and then want to solve over those parameters which define the affine policies, then there exists multiple local optima. And you essentially lose convexity when restrictions are placed on memory. And that's an important feature in a general stochastic control problem, where even the linear quadratic Gaussian problem, once you put restrictions on memory, so you lose convexity. And that leads to difficulties. The note, and this is a note that Witzenhausen formulated this as a two-stage discrete-time linear quadratic Gaussian control problem, except that control at stage 2 does not have access to what control at stage 1 had, so that's limited memory, or memoryless controller, but as I indicated, this can be reformulated as the one that I have. And the reason why I formulated this way will become clear shortly. Now, a policy that beats the best linear one is one which uses partial quantization, and this is a two-level quantization where you just look at the sign of x and then multiply it by some scalar epsilon, and then you use some linear term on x, and then once u0 is fixed to the structure, then you can find out exactly what the optimal u1 is. You optimize with respect to epsilon and lambda. The result is that this optimization will lead to an epsilon which is different from 0. So which means that the linear solution is indeed not optimal. And this is something that improves over that linear solution. You can actually go a step further and then say, why should I use a two-step? That was what Witzenhausen had provided. But you can actually use a multi-stage quantization. And the question is, can you do better? Yes, therefore, yes, indeed, one can do better. And the problem here is what's the best quantize that one can use here. That's still not that's still an open problem. The characterization of the best quantize given a fixed number of levels, but one can show that for fixed levels, then you can do better than a two-level quantize. Okay, so here's a problem. Even though you have a Gaussian channel and because of the nature of the quadratic cost function, you actually have to go into quantization necessarily in order to improve upon the linear. But I'm not saying that the optimum solution for this problem is necessarily a quantized solution, because Witzenhausen actually has shown that the solution has to be smooth. Now, if I break this into two parts, the simplest difficult problem, the Q function, I break it into two, u0 minus x, u0 minus u1. And I say, well, let player one, now we have two decision makers, it's an non-zero-sum game. Let u0 be involved in simply minimizing this, and u1 be involved in minimizing this. So this is a non-zero-sum stochastic game, and you can show that there exists a unique Nash equilibrium, but that unique Nash equilibrium is actually highly unfavorable to B in this case. And because u0 can make it the quadratic cost in this case 0, whereas the other one is going to be right. In fact, is one example that if we let sigma w squared is equal to this, there's a reason for this specific choice, and k0 equals to 1, this is in the Witzenhausen counter example, then the linear optimal solution for the Witzenhausen counter example, which is the sum of these two, will lead to gamma 0x equals to 0.67x, whereas for the Nash equilibrium, gamma 0 is x. So you can find the sort of price of anarchy in this case, which is the Nash equilibrium sum divided by the global minimum, and which is larger definitely than the Nash equilibrium sum over the best over linear pulses, and then which is about 1.33. So the price of anarchy is larger than strictly larger than 1.33 in this case. Now, exactly the same system, but I changed the cost function here, and the cost is the cost on u0 as well as now the u1 wants to find an estimate for x, and this is the so-called standard Gaussian test channel, and in this case we know, going back to the 1960s, that the solution is best solution is linear. So exactly the same system, but the quadratic function itself has been changed in terms of its structure, and then we made a difficult problem, a relatively simple problem, simple in the sense that the solution is linear. It's not simple in the sense that the solution is easily obtainable, derivable, because the only way I know of obtaining the solution is to compute the channel capacity and the rate distortion function, and then showing that this inequality is actually high in this case. And this is the only actually one of the few instances when static causal coding, and in this case linear, leads to attainment of inequality in this inequality. But so that's an indirect method, and there is no, as far as I know, there is no direct method for solving this problem. So what's the difference between the Gaussian test channel model and the earlier Witzenhausen counter example? So coming back to the Witzenhausen's example, we see that there is this cross term between u0 and u1, and that's what makes it difficult. And whereas in the Gaussian test channel you would have separate costs which do not involve a cross term between u0 and u1. So my conjecture here is that whenever you have a quadratic cost function which involves a product term between the decisions at different stages, and when they don't share the same information, then that's an inherently difficult problem. Now, going back again to the Witzenhausen's counter example, but now saying that let's look at it as a zero-sum game. And so in this case, I changed the plus sign to minus here, and now I'm maximizing with respect to one variable, that is the u0, wants to send as little information as possible, and then the gamma 1 wants to minimize, u1 wants to u0 to be this to be equal to u0. So here one can show that there is a unique saddle point solution, and the policies in this case are linear. So I have changed the team problem where there is cooperation, but cooperation, they don't share information. to one where there is no cooperation, and there is again no sharing of information, but the problem without cooperation is actually a simpler one. And I'm not, you can show that the linear is optimal in that case, and the best linear gain is solves a polynomial equation. So the recap is here you have essentially for exactly the same model, you have 4 different quadratic laws. For one, which is Whitson algebra, for example, as well as any which has where there is a cross term between U0 and U1, the best solution is nonlinear. We don't know what it is. And for all others, the Gaussian test channel or the one where you convert it into a Nash game, as well as the zero-sum game, they are all linear. So the upshot of this, the message here is that it's not only the information structure, but also the cost function that is a determining factor in whether a problem is simple or difficult and reasonable to be interpreted in the right way. Now, this paradigm, this is a 2-decision unit problem, but that's indicative of the kinds of difficulties that you will run into if you even look into problems with higher number of stages. So one could ask whether this would be extended to noise corrupted access to initial states, vector valued variables, the higher number of decision units, or to non-cooperative games. And just very quickly, if you have noise corruption, which means that in this case you have x plus b, but still you are interested in x, and gamma 0 is access to noisy version of x. Essentially, the structure with the results are the same, and nothing changes in this case. The other one we will just apply for simplicity. The vector valued variables, things are difficult. In the extension of the Gaussian test channel result, the vector valued variables does not carry over. The solution is not linear. There is a special class of systems where one can prove linearity. But the zero-sum stochastic game in the vector version is also tractable. So in some sense, that if you have go after worst-case designs, the worst-case design problems are simpler than T problems. This is one case where you have multiple channels that you can actually obtain an explicit solution, and a linear solution is this one. Still, there are 2 decision units, but in between these 2 decision units, there are multiple channels which provide information to gamma 1. Each one has a different scaling factor, and one can actually show that the optimal solution in this case, this is just the extension of the Gaussian test channel, is indeed linear. So I'm going to so this is the essentially the quadratic cross function in this case. So you have a U0 squared term. U1 wants to be as close to x as possible, and then there is a cross term between U0 and U1. But there is no cross term between U0 and U1, only between U0 and x. Okay, that's why this is right. And so another one, and this will hit the home front here, because I'm going to work on this problem. Let's consider exactly the same system with noise measurements. But now, instead of having 2 decision units, I'm going to include some real-life units here. Gamma 1 through gamma n minus. If you again have the WIs here, it's a Gaussian channel. Of course, if these gammas are nonlinear, then you no longer have a Gaussian connection between gamma 0 and gamma n. And then everything is Gaussian independent and so on. And let's say that the quadratic cost function is again the same, so which means that you want um to be as close to x as possible. And at the same time, you have some soft constraints on all the other decision units, the controls of the other decision units. So that's a very natural extension of the Gaussian test channel problem. And now the question is, well, do we have a linear solution. That is the best way to design these lemmas is simply to scale the output of these channels. And well, Lipsa and Martins, I think a former student who is also here now at IMF, have shown that for if m is larger than 3, then to a counter example that affine laws are no longer optimal. So there are nonlinear laws which actually lead to better solutions. So which means that the Gaussian test channel result is quite fragile. If you add additional units, then you no longer have the linearity. This is for n larger than 3, and they think that for n equals to 2 and 3, then it may be linear, but there's no proof. But there's no counter example. Now, another twist to this problem, which is that what I'm going to do is, instead of having a cooperative player, I'm bringing a jammer here. So this is an uncooperative player. And you can have multiple jammers actually. It could be the serial network I had earlier, and then multiple jammers. You can have gamma j have access to x. You can have gamma j have access to the output of at this point, or have access to the output of this channel. And with some constraints on J, and with k sub j's are faster. So here, what you want is you want to be as close to x possible. So which means you want to find an accurate estimate of what was transmitted or intended to be transmitted, with some soft constraint on u0, as well as some soft constraint on ug, but with a negative sign because the jammer is going to maximize, and then the other gamma 0 and gamma 1 are going to minimize. And this problem has a linear solution. Okay, so I'm not going to go over the details, but the saddle point solution in this case is linear. So again, here is an instance of a variation over the basic around the basic problem, where if you go in the direction of thieves, in other words, if you bring in decision units which will help with the transmission of information, more accurate transmission, then you end up with a very difficult problem. Whereas if you make it a jammer and say here is someone who is going to disrupt the transmission within some capability constraints, then you have a relatively simple problem. I mean, I'm not saying that obtaining the solution to this is trivial, but it can be shown that there is a linear solution. And once you have linear saddle point solutions, then because of you can show that any value, even a nonlinear solution will have to yield the same value, but actually a nonlinear solution cannot exist here. So I want to leave you with two messages as far as this part of the presentation goes. One message is on a variation of LPG. I mean, we think that LPG is very robust, this and that. But if you put restrictions on the memory that a control will have. In other words, in the standard LPG problem, you have the control has access to current value of y, measurement which comes from the sensors, as well as all the past values, and that's why you are able to count filter and so on, separation. But let's say that you have a moving window of some period tau, and you cannot go further back than tau beta. And this problem is an extreme case. You have the control as a function of y at time t only, and this is a very difficult problem in general. And this what I have presented so far is indicative of it, shows what the difficulties are. So the solution to this is not. And another message here is that quantization plays, if you want to improve in problems of this type with memory restrictions, if you want to improve over the best linear solution, then you have to use quantizers. Now, I'm not saying that the optimum solution is a quantized version, but you can definitely improve upon the linear solution, as several examples have shown, using quantization. So even though you have a completely analog channels and so on, you are behaving as though there is a digital channel. So quantization plays an important role in the construction of policies. In a sense, you have to use hybrid controls, quantized plus a continuous part. And several people have contributed to this line of research, and there are other several examples that where quantization actually does that. Okay. So I want now to move to limited actions and jamming problems, where the question is what, when, and how to transmit, control, and jam when you have limited opportunities. And just some of this is a slide that I had earlier, that what I mean by limited usage is that the controller communicates with the client on the intermittently, and this is the bound is 100 times, and then the sensor communicates with the control only intermittently, and the adversary disrupts or jams communication transmission intermittently. Now, it may be clear in the case of sensors and controllers why they would not, they would only interact intermittently as needed because of battery conservation, energy conservation, and so on. You may say, why should the adversary do the same? If you are taking the worst case approach, you may think that the adversary is limiting its power. Well, first of all, the adversary may not be limited its power. But the other thing is that if the adversary or the intruder disrupts the communication continuously, then it gets detected. So therefore, to minimize the probability, chances of detection, you have to do it intermittently to minimize the chances of being detected, but at the same time doing the harm on the system. So that's why putting such restrictions on the number of times an adversary will interact with the system makes a lot of chance. Yes?
You don't put any constraint on intermittent communication between the sensor and the plant?
No. One can put that also, but I'm not, at least not in this presentation.
Do you think it's not as important as the other?
I'm assuming that the sensor and plant are closer to each other. The sensor is actually part of the plant. If you think of it as a multi-agent problem, then the sensors maybe are parts of the plant, and the control is driving the sensors. Now the solution to all these problems, in other words, if you put hard bounds on the number of times the control or sensor and the jammer can act, are threshold-based optimal policies. In other words, the decision units in this case will look at what the information that they have, some norm of that information, is to test it against the threshold. And the threshold is generated offline, but it is time variant, not time invariant. But you have to keep track of how many opens you have left if you have so many opportunities. So essentially what one is doing is that you are generating events. Events are generated, which means the event is whether an action should be taken or not. And the generation of these events are driven by the actions themselves. So these are not events which are generated exogenously to the system. Okay, so that's what that coupling makes this class of problems interesting, and there are problems with non-classical information, but can be solved. So one class of problems that I want to discuss very briefly are those where there is we look into estimation with limited transmission. Just looking at this part of the problem. In other words, the communication between the controller and this unit, the controller and the sensor, and what the controller wants to do is just estimate what is sent by the sensor. So in a in a more clear manner, this is what I call an optimal estimation over a limited use channel, where you have a source, the source sends a stream of bits or random variables here, and then you want to encode it, pass it to the channel, and the channel will be used only n times, but you have n opportunities. Out of n opportunities, you use it only n times. And then it's going to be decoded, and then the user will have to come up with an estimate of this random, the sequence of random variables. Okay, so given that source and the memoryless channel, for a given message of like n, and the number of channel users n, with some power constraint over the encoder, what's the minimum attainable value of the average distortion, and what the corresponding T and D pairs. So that's the question. So I'm isolating this communication between the sensor and the controller and formulating it as an optimal solution. Okay, so the order of actions here at any time k, it's a discrete time problem, is that the sensor makes a measurement, and then they will have to decide. So that's the source, actually. I mean the encoder or observer. It has to decide on whether to transmit it and shape it, and then transmit it over. And then the estimator will generate the hat k, under which is the decoder. And then the estimation error is incurred, and we move to stage k plus. So that's what happens. And this is a problem which is dynamic and non-classical, because the user does not have access to the measurements that the sensor has made, and does not have any basis as to what the reason was why a particular bit was sent over the channel. So let's consider a special case. You have two strings, IID and no norms. Okay, so n is equal to 2, m equals to 1. So you have two random variables, IID Gaussian, B0, B1. They are zero mean, variance sigma squared. And you have a perfect channel, no norms. Okay, so the estimation error is B0 minus B0 hat squared plus B1 minus B1. And you can transmit only once. So what's the best transmission strategy in this case? The open loop sensor policy, by open loop I mean you schedule, you decide before you even make any observations. You say, when should I transmit? Which one? The first one or the second one? Since they are IID, it doesn't make any difference which one you transmit. So the error is going to be sigma squared. Now, a more intelligent sensor policy would be you observe B0, and then you say, should I transmit it or not, according to some criteria. And this is something which will be implicitly, which will be obtained as a result of an optimization. Let's say that the sensor transmits it B0 if it lies outside some interval alpha beta, and then does not transmit it otherwise. So which means that then the B1 will have to be transmitted. But the sensor doesn't know what the value of B1 is. So you can formulate this as a minimization problem over the parameters alpha and beta, and that's a well-defined problem that one can solve. And the interesting thing is that the alpha and beta turn out to be minus sigma sigma. You are in that interval, and the error in this case is 0.52 sigma squared. So using this intelligent strategy, not an open loop, it's a closed loop, you have 48% improvement over the open loop models, provided that this alpha and beta are appropriate. Now you may say, well, is this the best choice? Can I do better than not picking an interval there as a decision unit? One can actually prove that in this specific case, this is the best you can. So you have to, the threshold is this sigma, and you look at the value of B0. If it lies outside, if the magnitude is larger than sigma, then you transfer. Otherwise, you do not. So one thing that's implicit in this derivation is that the knowledge of no action is useful information. Why is it possible to improve upon the open loop policy? Because when the sensor does not send a bit, then on the other side, the user knows the reason why it was not sent. And that's additional information. So all these problems will have things of this sort that when an action is not taken, that conveys additional information to the others. That's what makes these problems interesting. So in general, this is a paper with a former student of mine, which actually appeared in a special issue which Nuno and several others edited. The best sensor policy is of threshold form. In general, it is not interval depending on the distribution of the statistics. It's in a measurable set. If it belongs to a measurable set, then you transmit it, otherwise you will not transmit it. And one can obtain recursively the characterization of that measurable set. I won't go into detail. So one question, for example, one may ask is you can use this as a design problem. Given a time horizon, let's say of length 100, I want to estimate the state of a zero mean IID Gaussian process with unit variables. And as a criterion, I say the cumulative estimation error should not exceed 20. So the question is, how many sensor measurements should I allow for? Well, if you use this open loop policy, which I talked about, then you have to make 80 sensor transmissions. If you use this other intelligent policy, then it turns out that, I mean, this is a curve that shows you the trade-off between M and the error, and it turns out that estimation error of 20 can be achieved with 34 transmissions. So instead of 80, we have 34 transmissions, which is about 58% improvement, and what can be greener than this? And you may say, well, what does a sample path look like? Here's how the one sample path for this problem looks like. These are the times when you don't transmit, and when you transmit, every time there is a jump, you transmit. So it's a fairly sort of an irregular structure. We have taken other sample patterns. Okay, you can extend this to noisy channels. There are other difficulties here. You have to send additional 1-bit information. With the noisy channel, of course, you don't know when the user does not receive something or receives something. It may reduce the noise, not because the other side has sent a bit. So therefore, you will have to do some hypothesis testing, or there will be 1-bit information from the user from the transmitter to the receiver to say that yes, the transmission did take place. So there is that sort of. So you can do control with limited transmissions, so between the controller and the plant. And best control in this case is again of threshold. Okay? I'm not going to go into the details here. And then the last thing I want to talk about is when the adversary disrupts or jams communication. And just will share with you, and this is actually a paper, this is the most recent one, which will be presented at the CDC, upcoming CDC. And so one formulation for these problems is the following. You have a discrete time system, but there is this additional parameter alpha sub 3, which is controlled by, which is a 0-1 variable, which is controlled by the jammer. So if alpha is 0, then the jammer will not, then it means that there is the control signal does not reach the time. If alpha is 1, then there is no disruption in communication. And then you have this constraint that the jammer can act only n times, so therefore 1 minus alpha k summed over an empirical time and should be equal to it. Okay, so what we are looking for in this case is a saddle point solution. You have the standard sort of repulse function, quadratic repulse function, and if it exists a saddle point, you're looking for the best control policy and the best jamming policy. And again, the solution, I'm not going to go into. In all these problems, you have the one approach towards solving them is to extend the state space. So instead of only time and state, you also have the number of remaining jamming instances, or the number of tokens that are left in your pocket. That you have to, has to be another variable to keep track. So the solution is when you use a dynamic programming recursion, you have to keep track of these three variables: the value of x, the value of s, and the value of t. And in the case of this zero-sum game, it's the Isaac's equation that one has to formulate, which one can solve it on the extended state space, and then the result is the following: there will exist a saddle point solution, and it's not a mixed strategy saddle point. One doesn't have to go to mixed strategy saddle point. And then there's a threshold curve, and the threshold curve depends on the value of the state x at each level, and then if absolute value of x is larger than this one, or this one is larger than or equal to this one, then the jammer will act. If it doesn't, then it will not act. So this is again of the threshold type, and what the jammer, and these can be computed offline. The threshold. I'm going to skip these. These are some curves which show how the threshold changes for different values of the system parameters. But I want to leave you with a message that we should take from here. And this is opportunistic sensing, what I would call opportunistic sensing, control and decision making, because you are not taking actions unless it is necessary. Okay, so limitations on usage leads in this case to event-driven actions, where the events are also controlled, or they are caused by adversarial action. So most of the literature on systems, control of systems which are driven by events, the events generated exogenously. Whereas here, this opens the door for sort of a new type of analysis where the events themselves are also controlled. Okay, so that makes brings in a coupling. So some general facts is limited memory leads to non-classical information structure. That's what we saw in the first part of the talk. If you have limits on the frequency of actions of players, that leads to non-classical information. And the decentralization also leads to non-classical information, as well as delays or disruptions in transmission. And furthermore, if you have private information for agents, that also leads to non-classical information. And one of the important questions there is how much should the agents reveal through their actions? And sometimes revealing too much may not be to their advantage, and sometimes it may be to their advantage. So these are all problems which fall in the realm of systems with non-classical information. So my last slide is there's no general theory or approach to multi-agent decision-making in non-classical information structure, and hopefully during the next 25 years here at ISR, there will be some breakthrough. And not all problems, one message is not all problems with non-classical information are intractable, so it's important to carve out those problems which can be solved, some with indirect methods. And what we have also seen that it is not only the information structure, but the performance index that plays an important role in tractability versus intractability. And when we have battery limitations and energy conservation in multi-agent applications, the non-classical information structure is still very alive today. And Whitson-Alden's counterexample and different sort of variations on it still provides the guiding light. So I'll stop here. we were actually surprised that we were first expecting big strategy solutions. And because of the threshold type of policies, that it turns out that the jammer cannot do, using mixed strategies was not able to do any better than you can. It's just the mathematics. It's to mix it. Normally, you're right, when we have discrete distribution, when you have discrete decisions, that is whether you should act or not, that's a 2-point distribution. Then generally you make the scales, the center point is mixed. But there are also matrix games with finite number of decisions where the solution is not mixed, it's real. So there's a bunch of examples where it's up.
I was just wondering, you mentioned convexity at one point.
Yes.
In terms of using brute force theory or numerical searches to try to find a solution, convexity is the key. And I was wondering if you could come up with any idea as to what of the features you're mentioning lead to more convexity.
Well, first of all, I mean, all problems with non-classical information are non-trivial. And what people have looked at is different ways of sort of obtaining better and better solutions to what's now the counter example. One approach would be to approximate the policies using artificial neurons. So you take a number of basic functions and then you multiply by gain parameters and optimize on these. And even there, the solution is not, you don't have convexity, and so therefore you can only have local solutions, but you can exhaustively search all possibilities. And Larry Ho and his group did some ordinal optimization and towards these problems, and that did not lead to all solutions. And there are also the Sahai and the students at Berkeley at different sort of levels of quantization from the information given.
Many of the things we discussed, what is of paramount importance is to what extent the control, let's say, function and the information gathering the sense function are coupled, right?
Good.
So if I abstract the problem where I don't think about states, because to some extent I have problems with, not with your talk, but the insistence on calling non-classical something that is non-classical because if I insist on the states, the way the states communicate are not what I used to do.
That's why I
want to
stood
abstract
away.
to measurements and just what is what you want to do overall. Even if you abstract in such a way so that it's time by indicating it as a problem. Then what is state? We will have to come up with a problem. An example that is very that in the end we saw that we need right?
Sure.
So if one formulates it this way, right, it's possible to get new artificial variables, which is called state, where we there have the problem becomes.
I don't think whatever you do, the Whitson algebra counter or something is not going to
You won't have the same structure though, because
It
I
will
don't
not-
expect the constraints to be the same.
well, it is, the question is, I mean, you can formulate, my formulation of this problem is reveals other sort of aspects of the problem, but it's exactly the same problem. I mean, it's a sort of mathematical transformation on that problem. So you have to change the problem itself in order to bring in these additional state variables if you are going to. So the important thing is that the first of all, the system itself shows non-classical information because the decision of one affects another one down the line, but that one doesn't have access. But not all these problems are as equally difficult. So what I said was that on the top of that, you have to have a coupling in the performance index between these different decision units which do not share information. So there are two aspects to it, the non-classical as well as this coupling.
Right, but from the perspective I described, the fact that you that not only the information partner is called, but also the cost are important, is not so surprising.
Yeah.
Because to some extent, the information partner is a little bit of an artifact, right?
Well,
to emphasize what I'm saying is the fact that you actually know that every existence of solution, even from 16, that you cannot compute anything, it shows you that maybe you're not looking at the representation of solution of the correct variables. In other words, you have a business of solution, but if you try to express it the way you wanted it, you can't.
yeah, but that's the problem you have. I mean, eventually you have to come back and you say, for example, the standard LPG problem with memoryless control. Can you solve it? And what I say here is that no, you cannot solve it. Because it boils down to this. Regardless of how you solve it.
Sense of solution, but let me
Well, you have to come up with a different.
That's a complication, but in other parts of science, right?
Yeah.
Let's say quantum information system, quantum problems. The way these problems are solved, when you get the same dilemma exactly, is you introduce supervisory systems or other systems that they help you.
If you introduce some additional terms.
But they come out of this abstraction. Once I formulate the problem, I have a complexity, the natural values of the problems are not the ones that start with it, because there, the coupling between sensing and information creates some sort of equivalent and assembly principle. In other words, you don't know where to go, because by the time you do, the other guy senses and acts, so it's impossible. Is that what happens here?
That's, if I can bring in a coordinator,
Yeah.
and I make the problem simple.
Actually, one of the
Yeah.
things we saw with the feedback, right?
Yes,
That's
yes.
exactly that.
Yes, I can bring the coordinator, but I would consider that cheating. That's taking a problem. Yes,
Two questions. In your Java model,
yeah.
if you restrict your Java to operate with a fixed battery life, let's say, now, the Java can choose to do the following. It can operate for a very short period of time with a very high power.
Yeah, right.
So it damage the
Yeah.
and so on and so on. But when does the model pick up that? That's one. And the second one is going to allow the legitimate parties to use the channel M1 or N times. Have you tried to look at a case where you fix the ratio N to N?
Yes, and then let it go to infinity.
Compare with information theory.
Simulation, well, we did it only through simulations, not theoretically. Yes, you in fact have fixed the frequency. M over N is N goes to infinity, goes to some small n. And then you do see some nice behavior. We haven't compared with that. To answer your first question, this is, I mean, I was interested in these because these are different. You have a fixed number of, like when the sensor wakes up and it goes back to sleep, then you have this finite number of times, and you know how much you are going to expand in terms of energy every time you wake up. So that's why I wanted to put R bounds on these rather than energy bounds. And the energy bounds is somewhat simpler actually in a sense. It doesn't have that. But that's also a soft constraint. This is something I had done way back with the Gaussian test channel with the jammer. There was a soft constraint on the jammer. Yes, John.
In this set of problems, when you have limited number of measurements,
Yeah.
just not limited, but just the source space computation. What is known when the system is done? Because some of what we have done here, that it's not actually a visualized threshold study. Because you have to solve a total time problem and you can't take a threshold.
Okay, well, that's why I said the threshold depends on X and on the number of times, number of on the information you have. Right. I mean, you have to, first of all, you have to have the model and the model of the system. But then your threshold, of course, I mean, I give you a number of tokens and you're spending it on times one. You have to know how many tokens are left and how many opportunities. If the number of opportunities is equal to the number of tokens in your pocket, then there is no problem. And so therefore the threshold is a function of what you have left in your pocket, what the horizon is, and what the outside measurements mean.
How many computers actually have when the X project is satisfied and say it's back to the Because even in the case of very simple linear models or most time will person and all that stuff, you can formulate that to actually solve it. But you can come approximately close by doing this piecewise constant threshold. This is close to what we described. But the optimal solution is always a stop time formalization process.
Yeah, that brings in the dynamics, brings in correlation.